So my key thing to you right now for this one is this cubed. That cubed is a problem, bless you, because for all of your trig identities, none of them say cubed on it. So somehow we have to knock it down a power. So when I notice that we have a tangent cubed, 99% of the time you're going to be able to factor it out in front. The only way we can factor it is if there's a tangent in every term. And when I say term, I'm talking about things that are attached by plus or minus. So I have a tangent here and a tangent here. Let me show an example where I could not factor it out. Let's say I had plus 1. This 1 does not have a tangent in it, so I couldn't factor tangent out of everything. Well, I don't have that 1. I just have a tangent cubed and a tangent squared that can be brought out front using factoring. So I'm now going to have tangent x times a quantity. Well, what goes here is basically tangent x times what would give me tangent cubed x. Well, that would be our tangent squared x that I wanted to create. And then we have minus. I bring that tangent out front, so what's left is the lonely secant squared. Now, if you're not sure if you did this right, just distribute this back and make sure you get this back out. Tangent times tangent squared, tangent cubed. Tangent squared times a negative secant squared would be a negative secant squared tangent. I pulled it out correctly. I'm also going to note for cotangent, I don't want to deal with a negative angle in the inside. Can't have that negative x here. So that's where you have to use those odd, even identities. I told you to memorize one specific one, and that's cosine and secant. For cosine and secant, you can just make this a positive. For everything else, you need to pull that negative out front. That's the only way to make that a positive, is to bring that negative out front. So now we have negative cotangent x. Now, I know we did a lot of times where we changed things to sine and cosine, but this isn't one of those. Instead, we should look at this tangent squared and this secant squared. Now, when I start seeing squared things, I think of my Pythagorean identities. And we have a Pythagorean identity that says that 1 plus tangent squared x would equal secant squared x. Well, it's close. I have a tangent squared and a secant squared, but I don't quite have it looking exactly like this. So I need to move this secant to this side, creating a tangent squared minus a secant squared. But that means I would need to put the 1 on the other side as well. So they basically have to switch places, which is then going to leave me with tangent squared x minus secant squared x equals a negative 1. So all of this just equals a negative 1. And what's a negative 1 times tangent x? Well, that's just negative tangent x. So we do all that kind of scratch work to get us down to negative tangent x over a negative cotangent x. Now, if you wanted to right here, you could change it to sine and cosine and you'd get the right answer. So if you're just like, I always change things to sine and cosine, it would get you the correct answer. However, you don't need to for this one, because I'm noticing tangent and cotangent are pretty close together already. So what I'm going to say is, okay, a negative divided by a negative is a positive, so I have a positive. I'll have a tangent x over, and instead of cotangent, I'm going to change cotangent to 1 over tangent x. Because if I do keep, change, flip, I'm going to have tangent x times tangent x over 1, which just equals tangent squared x. The correct answer was A, tangent squared x. Once again, don't change things to sine and cosine unless you're in a section that says you have to, or you run out of stuff to do. I have stuff I can do before I change things to sine and cosine, so I'm going to try not changing it to sine and cosine. That is like our backup now. That is our, when I'm out of stuff to do, I could change things to sine and cosine. It's just a tool in our tool belt. Doesn't mean we have to use it every single time. Yeah, Dylan.
I did simplifying it earlier, but I got negative sine x over negative cosine x times negative sine x, negative cosine x.
Yeah. Awesome. I'm just showing you that sometimes you don't have to change it to sine and cosine. That in fact, making it to sine and cosine can actually make things more complicated sometimes. All right, so I don't want it to be like, Okay, as soon as I have to do anything, I'm changing everything to sine and cosine. That's no longer what we need to do. That's just a tool we learned on the first day. That's one thing we can do if I need to simplify stuff. Questions on the bell work? So let's go over questions on the homework. We had 7.2a that was due today. Go. 19. I think I have it up here. 19 says 12 tangent squared plus 5 tangent x minus 2. We're supposed to factor each trig expression, correct? So if I was going to use factor by grouping, I would do my air conditioning and my Beyonce column. My air conditioning would be 12 times a negative 2, which would be a negative 24. My Beyonce column would be a 5. I think sometimes factor by grouping, the hardest thing is to come up with the numbers that actually work for this. So I need something that multiplies together to give me 24, but when added gives me a 5. You're saying 8 and negative 3. Let's check that out. So 8 and negative 3. Does 8 times negative 3 equal negative 24? I agree with that. Does 8 plus a negative 3 equal 5? Yeah, perfect. My suggestion to you, especially when you have a negative, just find two numbers that have a distance of 5, 8 and 3, and try a negative 8 and then try a negative 3 to see if it works. We're looking for that distance. All right, now the whole point of pulling out that 8 and negative 3 is that we are going to break apart that middle term. So I'm still going to have that 12 tangent squared x, but instead of 5, I'm going to have a plus 8. Actually, do you mind if I change these to x's and y's right now, just so I don't run out of room? I'm just going to change these to x, so we'll say that's x squared. And then we'll change that one to plus 8x minus 3x minus 2. Just speeds it up a little bit rather than having to write those signs. So picture this is just 12x squared plus 5x. Well, 5x split apart into 8x minus 3x. That works. Now we have two groups. Our whole point of factor by grouping is coming up with these two groups. Now we're going to factor the biggest thing we can out of each of these groups. So if I look at 12 and 8, I can pull a 4 out of both of them. I can also pull an x out of the x squared and the x. So that's going to leave me with 12 becomes 3x, because 4x times 3x gives me 12x squared. And then that 8x just becomes a positive 2. 2 times 4x gives me that 8x. Now, here's the rub on this one. If you can pull out a negative, see how this first term is negative? I need to actually pull out that negative 1. So I'm actually going to pull out a negative 1, creating a positive 3x plus 2. Now, I knew to do that because these terms need to be exactly the same. That's why I like this method, because it's a check. Hey, if both these are the same, I did everything correct. I just have to smoosh together the 4x minus 1 to create our 4x minus 1. So I smoosh together these guys times our 3x plus 2. And now I just put tangent x for whenever I see x. So I should have 4 tangent x minus 1 times 3 tangent x plus 2. All those steps make sense?
Yep.
All right, the big thing is just making your columns and understanding what's happening here, that I'm just trying to split that apart. I think once it's split apart, it's pretty easy. The factor by grouping just kind of works out as basic algebra. It's this part and understanding that why we're doing it. All right, more questions? Yeah, hold him.
Could you go with 3?
Sure. That's not 3. That's 3. All right, 3 says we're supposed to match each expression with one of the things below. I don't have the things below. Do I have the things below? I do have kind of the things below. Well, what I'm looking at here is what probably is going to happen is I'm probably using difference of squares. This is a minus b times a plus b. So I'm kind of picturing perchance, and I can't see it up there right now, but we should probably be doing something with cosecant squared x minus cotangent squared x. Now, I should probably remind myself that, this must relate to the fact that 1 plus cotangent squared x equals cosecant squared x. Well, if I move this cotangent squared to the other side, we would have a negative cotangent squared x, and this whole thing would just equal 1. Is one of them on the bottom? Okay.
That's the answer is 1.
That is how it equals 1. So my advice is anytime you see anything that looks like this, write down a Pythagorean triple or theorem that makes sense with it. Okay? If you're ever stuck, just write one of these down. And these need to be memorized. Okay, what else? Yeah, Jack.
7.
7, is that on this? Okay. So 7 has a nice trick to it. I don't know what I have down there. We'll figure it out. But this is what I would do. I would say, okay, cosecant, let's change those to sines. Okay, so I could change this to 1 over sine x minus sine x all over 1 over sine x. Now, I told you a trick to get rid of fractions, and that's to multiply by its denominator. So if I want to get rid of that 1 over sine x in the bottom, I would just multiply the bottom by sine x. But you can't just do it to the bottom, you have to do it to the top. So I'm going to multiply the top by sine x as well. So now when I distribute this, this is going to equal sine x over sine x is just 1. Sine times sine is sine squared. And on the bottom, we just have sine x over sine x, which just equals 1. Are you okay with that so far?
Yeah.
Now here's the thing. Don't forget about sine squared plus cosine squared equals 1. Now in your head, if you picture you move that sine over, I would have 1 minus sine squared. So this whole thing should just equal cosine squared x. Is that one of the answers in the bank?
Yeah.
Okay, then that would be your answer. Does that all make sense?
Mm-hmm.
I like this trick. This trick can actually make verifying some a lot easier, where this could have been a several step item. So this could have been, let's not go through that. This is just the best way to do this one. I'm looking at another method, but it'd be like step after step after step, which you don't want to see. All right, more questions?
I think I accidentally did that method. I way too much work on it. So.
Yeah, did you get the answer? Yeah, there's no right and wrong way to do these as long as you're following proper procedures, proper things. Yeah. Sorry, Drew. I'm staying with Dylan for a second. Yeah.
When you go through a procedure and you kind of realize that you went down the wrong loop, where do you restart from? Do you just kind of restart?
You might restart from the beginning.
Yeah.
And my advice is, especially so if you're on a test and it happens, I would ask for a separate sheet of paper. I wouldn't erase everything because there's probably good stuff on there. The worst thing I see on tests is people erase an entire thing and they don't have time to finish it, and I circle things that were correct, but I can't give you credit for because you erased it. So if you went down the wrong path on a test, I would ask for another sheet and just try it again on a separate sheet.
I'll occasionally simplify a sine or cosine before I can, or I'll forget that 4 is 2 squared.
Yep, that little stuff. That's when you get another sheet of paper a lot of times. Okay, Drew.
Can't you split that up?
We could split that up. So you could split that up into, and you'll get the same answer. So you could split this up. I just wanted to show this little trick. But Drew is 100% correct that we can split this up. Does everyone that wants that has that down? And it's a good trick to see too, is that I can split this up because we're adding or subtracting in the numerator. If you're adding or subtracting in the numerator, you can rewrite this as cosecant x over cosecant x minus sine x over cosecant x. And now we have our 1, and we're going to find out that sine divided by 1 over sine just equals sine squared, and we end up with the exact same answer. Yeah, that's a great way to see that too. Yeah.
So you can never just look at it like that and cross out the cosecant x over cosecant x?
Correct. So I think you're saying you can't just do this.
Yeah.
You can't do that because of this subtraction, because it can be split. If this was a multiplication, so let's say I have a multiplication instead of a subtraction, the reason we're allowed to subtract that out, because this is really, you can actually move stuff around with multiplication to be this cosecant x times sine x over 1. You can push things around with multiplication that you can't do with addition. So if they're attached by multiplication, you can cross it out. It was subtraction or addition, you have to split it apart.
Okay.
If you're going to deal with it that way. All right, other questions? That's it? Okay. Then today we're going to do more verifying stuff. Actually, before we do that, let's talk about, we have a quiz on Tuesday. I do see you on Tuesday. We have a quiz on Tuesday. The next time I see you, we have a quiz on Tuesday. Now, I'm showing you the very first thing that will be on that quiz. This isn't the whole quiz. This is the very first thing. It looks a lot like that sheet that you have, except there's missing stuff. It'll be your job to fill in that missing stuff. It's actually not a ton of memorization as long as you know that cosecant goes with sine and 1 over sine equals cosecant. A lot of this is you should already know.
Is that the same sheet that we have?
This is the exact same sheet you have. The only difference is I just erased all the stuff on the left-hand side. So as long as you know tangent equals sine over cosine, cotangent equals this, understand how the odd-even functions work, that if it's cosine, you just make it positive, secant positive. For sine, you bring it out front. These, you need to know all 3 of them. No variations, just the 3. Just the sine squared plus cosine squared equals 1, the 1 plus tangent squared equals secant squared, and the 1 plus cotangent squared equals cosecant squared. If you get this stuff wrong, it just means you're not studying the stuff. That's all it means. You can't go, I'm bad at math, that's why I can't memorize basic things. Right after that, they're going to have like 3 or 4 problems that say simplify. I picked rather easy simplifying ones. I really just want to know, can you do this simple stuff? Then you have one example. Now, this is going to be the one that a lot of people get wrong. I pulled a problem out of 7.1b, where I say tangent of alpha equals 1 over 3, and alpha's in quadrant 2. Find the rest of your trig functions. That was the one where you had to use like 1 plus tangent squared equals secant squared, plug it in, and solve it. If you don't know what I'm talking about, go back to 7.1b. There is one of those on there. And then we'll have one pretty simple verify one. That's the quiz. All right, that will be on Tuesday. All right, any questions on the quiz? Yeah, go.
What we learned today, will that be on the quiz?
Well, we're doing verifying today, but we're not going to have as advanced ones. It'll be a pretty easy one. All right, if you know how to simplify stuff and you understand how to verify stuff, the simplifying will be enough. You'll just have to simplify one side. No big tricks or anything. It'll probably be you can change it to sine and cosine if you want to, and you'll get it done. All right. Today we're going to learn kind of more advanced techniques for verifying equations. So let's make sure our computers are closed, unless we're 100% certain. That's not closed. That's like tilted. Thank you. All right. So we already talked about verifying stuff. We did 2 of them from that homework. Verifying is we have an equal sign between them. It's basically the same thing as simplifying, except you know where you need to simplify to. I say you should choose a side to work on. Choose the more complicated side. It's just easier to simplify stuff than to make it more complex. Then my step 2 is, hey, do all those tricks we have to simplify it. So some tricks to simplifying it is you can write the expression in terms of sine and cosine. We are not going to do that every single time. That's just one of the techniques. It's like a hammer. If you got a nail, you can hammer it in. If you have a screw, you might choose one of these. Or we can use a whole mixture of all of these. So the first one is multiply the numerator and denominator of one expression by the numerator or denominator of the other. Yeah, we didn't do too much of that. We'll talk more about that at another time. But step 5 is something that you need to look at, and Drew actually pointed out today. If you ever have a plus or a minus in your numerator, you can split it apart into 2 fractions. So if I have sine x plus cosine x over sine x, and I run out of stuff to do, I can rewrite this as sine x over sine x plus cosine x over sine x, and suddenly it looks a lot different, where I have a 1 plus tangent. Like I can definitely change the look of that. So if I have a plus or minus in the numerator, I can split it apart as long as they keep that same denominator. Keep that in mind. That's a big one. That's why I wrote that down. That's why I gave you space to write it down. If you don't want to write it down, that's on you. Step 6 is combine the sum or difference of 2 rational expressions into one rational expression. That is really just push fractions together. I ran out of room. Push fractions together. So rather than splitting them apart, I would go the opposite direction and put them together. That involves multiplying the fractions by the other denominator. Multiply it by the other denominator. And then 7 says, hey, sometimes you'll have to work both sides. You have to work them independently. You can never move one thing to the other side. But sometimes it's nice to get a start on one side and then work on the other side to make them work. Most of them you'll be able to just work on one side, but sometimes it's just easier to do that. There's one technique that I didn't put on here. It's very similar to multiplying the numerator or denominator of one expression by the numerator or denominator of the other. That is this type of problem. So you might tell me, hey, we could break this fraction apart, and I'll agree. That could be a valid step. But I see something first, and it's something that you need to start seeing. I see a Pythagorean. I see something that's close to one of those Pythagorean identities, because you have that 1 plus sine x and you have that 1 minus sine x. And what I'm thinking about, if this was just 1 plus sine squared, or if this was 1 minus sine squared. Hey, if this was 1 minus sine squared, that would equal cosine, and I'd pretty much have that really simplified. So I'm looking at things that are very, very close to being Pythagorean, one of those Pythagorean identities. So, we've done this before. I said if you ever see a 1 plus or minus sine, cosine, tangent, cotangent, any one of those, you can multiply by the conjugate to force it to be squared. Now, do either of these sides look necessarily more complicated than the other? They look very close. So, someone tell me to work on the left side or the right side. Doesn't matter.
Right.
One more time.
Left.
Right.
Left. Overwhelming left. Overwhelming left.
It was, and then the right. I'm going to go left.
Yeah, boy.
I'm going to go left just because I have a little bit more room on the left-hand side.
Yeah.
Okay. All right, so let's take what they gave me on the left-hand side. So I'm also going to, I have plenty of room, so I'm going to go ahead and put a line down it. So I'm going to say, the line is not necessary. It just lets me know that I'm working on one side or the other. The line is not necessary. You can just put equal signs if you want to. It's just my personal preference to have a line that tells me I'm working on the left-hand side. So they gave me cosine theta over 1 minus sine theta. Now, I said this looks interesting because that's close to one of those Pythagorean identities where I can have sine squared plus cosine squared equals 1. Well, that means this has to be sine squared. To create a sine squared, I'm going to multiply by the conjugate. The conjugate is basically creating a difference of squares, where if I have 1 minus sine theta, I'm going to multiply by 1 plus sine theta. And what I do to the bottom, I have to do to the top. Just like what you do to the left-hand side, you have to do the right side. This is how I keep it balanced. So what I multiply on the bottom, I'm going to multiply on the top as well. Now, here's a bit of advice. Most of the time, you don't want to distribute first. You just see what it looks like undistributed. Because a lot of times, things will cancel out without you distributing it. So I am not going to distribute the top. I'm just going to put the cosine out front. And so on the top, I have cosine theta times the quantity 1 plus sine theta. Now, I harped on difference of squares a lot, almost every single lesson, because I don't want you to have to distribute this whole thing out. I want you to realize that this is a plus b times a minus b, which means you're going to have a squared minus b squared, which would be 1 squared. If you want to, you can put your squared on it. I usually just put a 1 now. So it's 1 squared minus sine squared. Bless you. What does 1 minus sine squared equal? It equals cosine squared. 1 minus sine squared equals cosine squared. If you don't realize that now, you have to keep writing it over and over. And that is the fact that sine squared plus cosine squared equals 1. If I move the sine over here using subtraction, has cosine squared equals 1 minus sine squared. That's what I have. So we now have cosine theta times 1 plus sine theta all over, instead of 1 minus sine squared, we're going to replace that with cosine squared theta. Oh, we're looking real close, aren't we? Because I have my cosine, I got my 1 plus sine. The only thing we have to realize is if I have a cosine theta on top and I have a cosine times cosine on the bottom, kind of like if I had x over x squared equals 1 over x. The same thing's going to happen with the cosine and that cosine squared. That I'm going to knock that power down because this will knock one of these out. So now all of a sudden I have 1 plus sine theta all over cosine theta. So here's an important part of multiplying by the conjugate. If I ever need to turn sine into cosine, the conjugate's the way to do it as long as it's already a 1 plus or a minus. So as soon as I notice 1 minus sine, I'm thinking, well, if I multiply by the conjugate, I'll have cosine squared. And that should help me knock out that cosine there. Conjugate's probably the most forgotten thing in class. Noticing how to do that. That can save you a whole bunch of time rather than splitting things apart. Most of the time, when you see something that looks like this, 1 plus or minus something that's not squared, it's usually a conjugate problem. All those steps make sense?
Yes.
Okay. I hope they do. On our next one. We have a whole bunch of different ways to do this one. In fact, let's go back in time. Drew told us that we can split apart fractions. And for this one, it really, really helped us. So let's try the exact same thing. I'm actually going to show 2 ways to solve this one, just like I showed 2 ways to solve the other one. So I'm actually going to make kind of a, try not to run into, I'm going to have like an area where I'm not going to write into the right of it. So I'm going to work on the left-hand side because I'm pretty sure that looks more complicated than the left-hand or the right-hand side. I'm going to split apart this fraction. I'm going to have cosecant x over sine x minus sine x over sine x. Well, one of those fractions is really easy to deal with. And that's that sine x over sine x, that just equals 1. So I can already go down here and I can write a 1 there. Maybe I should save myself a little bit more room. All right, cosecant over sine x. Well, cosecant is just 1 over sine, right? Cosecant is just 1 over sine, so I could rewrite this as 1 over sine x divided by sine x. Now, here's where people make mistakes. We can all say that same keep, change, flip. Keep, change, flip. Keep the top, flip the bottom. But here's a very common mistake that people make. And I'll do that off to the side. So keep is easy. Keep that top part the same. And what I see a lot of times is when you flip the bottom one, you leave it alone. Did I change my denominator at all? No, I didn't flip it. Very common mistake is to not flip it because you don't see that there's actually a fraction here. There's a fraction here. It's sine x over 1. So keep, change, flip would actually make this 1 over sine times 1 over sine x because this is sine x over 1. You always have to change something when you flip it. So if it stayed the same, you made a mistake. So now we have 1 over sine times 1 over sine, which equals 1 over sine squared. Minus 1. Well, 1 over sine squared is just cosecant squared. X minus 1. And 1 plus cotangent squared equals cosecant squared. So what does cosecant squared minus 1 equal? It equals cotangent squared. So we are done. That this just equals cotangent squared x. And once again, if you want to write that out, write it all out. Yeah. Yeah, go ahead. So I can split apart the fraction and it works. Let's do this a different way. Let's say I started the problem, I just noticed that cosecant kind of stands out. Everything else is terms of sine. What if I just change the cosecant? So here's like an alternate world we live in. We're going to say, I saw this first. I saw the fact that I can turn cosecant into 1 over sine first. And then you remembered that trick that I taught you, that if you want to get rid of that fraction, that 1 over sine fraction, I can multiply the entire top by sine x, which means I need to multiply the bottom by sine x. This is understanding how to clear fractions without doing keep, change, flip. I'm just going to multiply the entire top by sine x, which means I need to multiply the bottom by sine x. Go.
The only reason you do that is so you get sine squared, so you can make that cosine.
Yeah, well, realistically, I'm just saying, how do I get rid of this fraction? This is one way, but I'm going to start seeing that I'm going to get sine squared, so I'm going to get things that I want. All right? So originally, I'm just like, how do I get rid of that 1 over sine? Well, one method is to multiply everything by sine. So that's going to give me sine over sine, which would give me 1. Sine times sine would be sine squared x, all over sine squared x. Now, 1 minus sine squared we can replace with cosine squared x. And cosine squared over sine squared equals cotangent squared x. So all of these have multiple ways to go about them. As long as you're doing valid steps, there are times where you do valid steps and you just get stuck. That's when you go back and you try something else. But both of these worked in this case. So it's good to know multiple different approaches. Because you might have did this approach and made a mistake and said, oh, this just equals 1. 1 minus 1 is 0. Let's try something else. It's always nice to have another way to solve a problem. So my 2 big ways up here are split fractions apart, get rid of fractions by multiplying by the denominator. 2 big things you need to know how to do. All right, example 3. Which side looks more complicated?
Right.
Probably the right side. There's always one, isn't there? There's always one, isn't there? I'm going to work on the right side just for the fun of it. What kind of problem does this appear to be?
The not square roots. There's Pythagorean identities.
There are Pythagorean identities that are hiding in there because I'm like, okay, I have a cosecant minus 1, I have a cosecant plus 1.
Difference of squares?
Difference of squares.
We're going to look for difference of squares. And the nice thing is, this is how these always work. What should I try to do if I have 2 fractions? Push them together. And guess what happens? If you look at this, these are actually conjugates of each other. So even if we know we're multiplying by the conjugate, this will force us to multiply by the conjugate as well, because I need to multiply the top and bottom by the other denominator. I know some people like to just show that by just putting an arrow going to both things. I'm going to actually write it out, but some people just draw an arrow saying take the denominator and put it to both things. I'm going to draw all that out. You write as much as you need to write. So I'll write what I was given. I was given 1 over cosecant x minus 1. Multiply by the other denominator. So I'll multiply the top by cosecant x plus 1. And I'll multiply the bottom by cosecant x plus 1. Sorry. Then I was given a negative sign. And then I was given a 1 over cosecant x plus 1, multiplied by the other denominator. The other denominator is cosecant x minus 1. And this one is cosecant x minus 1. So it's good to know conjugates and difference of squares right now because you understand that I'm probably doing something right. Now on top, distribute that 1. Well, our top, 1 times cosecant plus 1 is going to be our cosecant x plus 1, divided by a difference of squares. A minus b times a plus b equals a squared minus b squared. So this will be cosecant squared x minus 1 squared, or just 1, minus cosecant x minus 1 divided by cosecant squared x minus 1 squared, or just 1. Yeah, you know how to do this one? Okay. All right. Now, I picked this one in particular because there's an easy place to trip up right here. And that is when I actually rewrite this. Because most of the time people don't rewrite it. They just cross things out. I'm going to rewrite what happens here. I'm going to actually do the subtraction. So I have cosecant x plus 1 minus that cosecant x minus 1 all over cosecant squared x minus 1. Take a second and find my mistake. That is incorrect. And it's going to be a mistake that a lot of you make. Drew?
Do you have to combine the two denominators?
I don't need to combine the... I did that right. So when you subtract something or add them, the denominators just stay the same.
Is it the double negative?
It is the double negative. It is the fact that I am subtracting this entire fraction. That subtraction goes to both items. I am not only subtracting cosecant x, I'm subtracting a negative 1, which makes it a positive 1. Which means the top will not be 0, because some people will say it's 0 and they'll be done. It would not. It would be...
2 over cosecant squared x minus 1.
Yeah, and I'm actually going to change something real quick. So I'm going to notice that these will cancel out. Berm. I have my plus 1 and plus 1, which is going to equal 2. But I'm going to shortcut something here. Cosecant squared minus 1 sure looks like a Pythagorean identity. What is 1?
Cotangent squared.
Cotangent squared? Are we positive?
Yes.
Let's check it out. So I would have, if I was on a test or something, I just to make sure, I would write out what it looks like. Well, we have 1 plus cotangent squared x equals cosecant squared x. To get a cosecant minus 1 means I need to subtract a 1 from both sides. It does just equal a positive cotangent x. The big thing that trips people up is sometimes it's negative and sometimes it's positive. Well, 2 over cotangent x is the same thing as, well, what's 1 over cotangent x equal to? Tangent. So 1 over cotangent squared would be tangent squared. And this is actually 2 times this, so this would be 2 tangent squared x. Done. Bing, boom. Done. Yes?
Could you explain how you got that again?
Which, from here to here?
Yeah.
So what I was looking at is, instead of picturing this as 2 over cotangent x, I'm actually picturing this as 2 over 1 times 1 over cotangent squared x, because that 2 can just be pulled out front because it's attached by multiplication. Now I'm going to remember that 1 over cotangent equals tangent. So 1 over cotangent squared equals tangent squared. Okay? So basically, if they have any number on top of like a cotangent sign or anything like that, you can always write it as a non-fraction. So if I had 4 over sine, I can make that as 4 cosecant because it's reciprocal. Okay?
Yep.
And if you ever get stuck by that, work on this side a little bit. Because you'd be like, oh, you know what? Tangent squared is 1 over cotangent squared. Oh, that 2 is just going to go up there. Okay, that matches. So if you ever get stuck somewhere that looks really close to this, just look at the other side and see if that helps you get there. Preguntas. Okay, we just have one more example to go through. So there's a lot of good things happening today that we need to keep track of. All right, our next one. I'm going to work on both sides to start off with because you cannot have those negative t's. So now we have to remember, for cosine and secant, you can just make them positive. For everything else, they got to come out front. So for this one, this negative has to come out front.
It's gonna be positive.
It's going to be positive. So I have 1 minus sine squared t all over 1 plus cosecant t. For the other one, because sine, you bring it out front because that odd even. So this one's going to be 1 minus sine t over cosecant t. Here's my thoughts on this one. Look at both sides. They both look seemingly complicated. Maybe this one looks a little more complicated. I'm actually going to work on this side. And the reason why I'm going to work on this side is because I'm going to see the only difference between this top part is there's a square here. How do I turn 1 minus sine into 1 minus sine squared? I multiply by the conjugate. So that would be my first thought, is multiply by the conjugate. I see that 1 minus sine, and my immediately thought is, let's multiply by the conjugate. So I have 1 plus sine t on the bottom as well. This is a minus b times a plus b. This is just a squared minus b squared, which would be 1 squared, minus sine squared. All over, I'm going to go ahead and distribute that cosecant to both things. So this will be all over cosecant t plus sine t cosecant t.
Would there still be a t on the top?
There would be a t on top. Sorry. I sometimes drop those because it's easier to write. But thank you for pointing that out. We're really, really close. We're really, really close. The big thing you have to realize here is, what happens when you multiply a number by its reciprocal? What's 2 times 1/2?
1.
What's 4 times 1/4? What's sine times 1 over sine? It's going to be 1. That should just be 1. This whole thing is just, yeah.
How'd you get sine t times cosine?
Cosecant t, because this has to get distributed to both things. That cosecant needs to go to both items, because that's why I put those parentheses there.
Oh.
You okay with that?
Yeah. Yeah.
You sure?
Yes.
Okay. All right. So I have sine t times 1 over sine t, which just equals 1. So that's really just a 1, which means we're done. I have my 1 minus sine squared t on top. I have a 1 plus cosecant t. Notice I just flipped these, kind of like if you have 2 plus 1 equals 1 plus 2, just to make sure it looks like the other side. And you are done. This takes what looks like a very complicated problem and makes it really easy as long as you realize that it's just a conjugate. Here's a couple things I want to talk about for working on these. I don't give you a lot of space to verify them. It's kind of a small space because I don't want to print out 50 pages for each of these. Either write small or write on a different sheet of paper. All right, if you can't fit everything in there, write on a separate sheet of paper. But just assume that you're going to have enough steps to fill it up, so write small. My second thing is,